Okay? And so that's given as Ro-Vibrational Spectroscopy. In other words, gas phase FTIR. Okay? So let's get into that. And this is one of my favorite things to describe because there's some really good classic physics going on here. And I like to think of this phenomenon as the quantized ice skater. So we'll call this here the quantized ice skater or quantized figure skater, however you want to think of it. Okay, so let's go back to the basics. All right, so we recall that our Morse potential, right, this potential energy curve, that really represents the entire ground electronic state, right? And so you did this on your exam, right? You calculated the energy of the one sigma level, right? This would be that electronic energy level, okay? So we recognize that here is the ground state, nu equals 0, where we expect most molecules to be. Here is nu equals 1 and 2 and 3. And within this ground electronic state and ground vibrational state, there are J levels. Okay, so there are rotational J levels. And so here you can see as a much better zoom in of that, where at the nu is equal to 1 state, I will have a population of rotations, right? Especially if this is a sample at room temperature. Also within, and so we call that J double prime. So the J double prime right here, those are the J levels for the ground state. So then now in the vibrational excited state, there are also a population of J states, and that's given as J single prime. Okay. Let me find my place here. Okay. So what's happening with this quantized ice skater is kind of like what we described with bond distortion when I was talking about microwave spectroscopy. So if you imagine a fully elongated bond, right, it's stretched out to here, and it's rotating, all right? It's going to be rotating at some given, frequency based on the molecule's rotational constant and, of course, temperature. But now, as that bond vibrates and comes in, the molecule is going to rotate faster. As it stretches, it's going to rotate slower. As it comes in, it's going to vibrate faster. And so this process is going to be very dynamic, right? It's going to slow and then increase, and then slow and then increase. I could do this all day long until I get too dizzy, which I think just happened. So what happens now is this molecule elongating and compressing can stimulate the rotational levels. Okay, and so that's what you can see with these arrows right here, right? Where we might have, a molecule going from the ground vibrational state in the ground rotational state, right? That would be this point right here. And as it goes through some excitation, the vibration actually excites it a J level. Okay, so you can see now it doesn't go directly to the nu equals 1. It goes to certainly to the nu equals 1, but it goes to the J equals 1 within the nu equals 1, right? And so you can see now from these other arrows that all kinds of other possibilities exist. So let's organize all of those possibilities, okay? And so they are organized into what's called the P branch, the Q branch, and the R branch. And I want to really keep in mind, I want to stress that this is gas phase, okay? We don't observe this phenomenon in liquids or solids because as you try to rotate a liquid or solid, there's another molecule in the way, right? There might be another molecule that it's hydrogen bonded to, right? That's preventing it from rotating. Or certainly in a solid lattice, you can imagine how that will prevent a molecule from being able to rotate. So we only see these types of transitions in FTIR with gas phase molecules. Okay? So let's be very clear about that.